Ready to harness the power of your communications data? Blast off with Nylas today.
Hello and welcome to Coding with Nylas, the live stream where we talk about programming, APIs, and more. My name is Blag, Senior Developer Advocate here at Nylas.
And my name is Ram. I'm a developer advocate at Nylas too.
So how are you, Ram?
I am doing good. Maybe a bit tired from all the snow. We were just talking about that. How have you been? We haven't live streamed in some time.
Yeah, we have kind of like some sort of vacation. I've been doing fine, thank you so much. I was just missing doing the live stream. So it's cool to be back.
Oh, well, I'm excited for today's topic. How about we jump right in? What are we talking about today?
So we're gonna talk about quantum computer. So it's gonna be kind of like a gentle introduction. Uh, and we start with this kind of like a joke, like a Boolean in quantum computers is like true, false. How do you call it? True.
Fru? Is this Fru?
Yes. So it's you don't know what it is actually. So true. So what are quantum computers? So quantum computers rely on naturally occurring quantum mechanical phenomena, which is basically superposition and entanglement. And we're gonna see in a bit what that is. Those states can speed up computation on complex sets of data, so it can be pretty fast. And while classical computers use bits, quantum computers are going to use qubits. So, what is that? So, a classical bit can be either 0 or 1. A qubit can be 0, can be 1, or can be both at the same time. And that's superposition. So, it can be either of the states. Um, that's kind of like the formula to represent it, right? So 0 plus 1 over a square root of 2. Okay. So we also have entanglement. So entanglement means the pair of a group of particles are linked together and they cannot be discussed separately, even if they are like million years away from each other. So let's say we have these two boxes. Inside, there's a red ball, and the other one have also a red ball. If we're not looking at the boxes because the boxes are closed, the balls can be either red or yellow, or it can be both at the same time. Let's say I open this first box here, and I see that the ball is red. So when Ram opens the second box, the ball is going to be red for sure, like 100% red. But then we close the box, we go to drink a coffee, then we go back. Then Ram is going to open the same box that I opened. But now the ball is going to be yellow, which means if I open the second box, it's also going to be yellow. So what happens if we both open the boxes at the same time? It really depends on which one of us is opening that. I mean, there's going to be always like a microsecond that one of either of us is going to open it first. So the first color that we see, the other ball is going to be exactly the same color. This is kind of weird, but that's how it is. Even if the balls were separated, like I'm in Canada and Ram goes to Germany, for example, we open the boxes, it's exactly the same. Red ball, yellow ball, yellow ball.
So I guess the quantum, the qubit here is it could be either color or it could be shifting colors. And as well, they're always going to be representative of each other, irrespective of space and time.
Yes, exactly.
Okay.
So when you're not looking, you have no idea what it's going to be. So it's
Gotcha.
good. So why it would matter to us? What is be important for us? Because quantum computers can handle a lot of data in a real fast way. Although quantum computing is not suited for any sort of problem. So we can see the computer it's gonna kind of like execute things step by step. Quantum computer can do multiple things. So it's like kind of like multi-threading, but in a more speedy way, let's say. So what can we use it for? So these days they are using quantum computing for machine learning, optimization, biomedical simulations, financial services. So the only caveat is that for a real quantum computer to operate, you need a temperature of 15 millikelvin, which is roughly minus 273 Celsius or minus 459 Fahrenheit. So they need to operate it in Canada probably in the winter.
Perfect location.
So people might tend to think like, oh, I can do everything on quantum computing and it's going to be super fast. Not that always. I mean, it's not like everything that you do, probably it's going to be even slower on quantum computing. It needs to be certain scenarios that it's going to be faster, that it's going to be better, but it's not for everything. It's not going to replace all computing in one spot. Also, it's very expensive to actually use a real computer, right? Like I was telling you, Ram, there's a company called The Wave where you can use up to 2,000 qubits, but it costs like $15 million. So you're not going to have it in your fridge, in your kitchen waiting to be used, right?
Gotcha. Okay.
But we can use it now. There's a library called Qiskit, which you can install in Python, and it's an open source framework that can handle up to 24 qubits. There's also one for Java that I'm probably going to mention when I write the blog about this introduction to quantum computing. But I find that the Python version is a little bit easier to use than the Java one. And both are pretty cool, but I like this one. So for demo time, first we're going to do the Bell state, which is one of the most simple, but kind of like the most important in quantum computing. It uses 2 qubits and it showcases entanglement, meaning that if one qubit measures 1, the other one is going to be 1 for sure. If the first one is 0, the second one is for sure going to be 0 as well. So let me share my screen and hide this. And hopefully this is going to look fine. So Python state, quantum Bell state. So when I run this, and I'm going to try to make this bigger so you can see it bigger. So here we have the first qubit and the second qubit. I'm not sure in my screen, or am I?
Yep. It looks good.
Yeah, to make sure. So the first thing we're going to do is we're going to apply a Hadamard gate, which is going to create superposition. So it's going to kind of like make the qubits have both states. We're also going to create a CNOT gate, which is going to create entanglement. And then we're going to measure both qubits here and here. So both are going to be either 0 or both are going to be either 1. So when I close this, we're going to see the second graphic. And this is telling us that we have a 47.7% chance that both qubits are going to be 0, and a 52.3% chance that both qubits are going to be 1. Which means if we have the 2 qubits in a box and we open the box, this is the chance that we have of them being both 0 or both 1.
So here, what you're showing is also like the randomness that's available in quantum computing, where it's not going to be one or the other. There's the randomness that's introduced. It could be 0, 0, or it could be 1, 1.
Exactly.
Okay.
So now let's jump at the source code. So here we need to first install from Qiskit. We need to install quantum circuit, quantum register, quantum classical register, execute, and basic IR. When we're going to see what that is. We also need to import a visualization tool from Qiskit, but also we're going to need image from the Pillow library, which is going to allow us to display the image. And we also going to need Matplotlib in order to showcase the first graphic that you saw, which is this one here. So for this one, we're going to use Matplotlib. And what we're going to do, if we're going to register 2 quantum qubits, and we're also going to register qubits. So what we're going to do here is we're going to use a quantum circuit to grab the bits and the qubits and create a quantum circuit. Then we're going to use the Hadamard gate to create superposition, and we're going to use the CNOT gate to create entanglement. So superpositions mean that they can be either 0 or 1 or both at the same time. And entanglement means that both the first qubit and the second qubit are going to be entangled or linked together. Once we have done that, we're going to measure the value, which means are they both 0 or are they both 1? Once we have that, we're going to execute a job. So that's where we're going to use this basic AR. We're going to use the the QASM simulator, and we're going to try. Oh, sorry, from bottom. We're going to try this 1,000 times. Then once we got the result back from the job, which executed the 1,000 times, we're going to draw the bell state. We're going to display it on the screen, and then we're going to do the histogram, which is the image that we saw with the percentage. We're going to save it, and then we're going to open it to show it up.
So one thing to call out here is you're doing this on your local machine. So this is a simulated environment of what a quantum computing machine would do. So to actually get the results of quantum computing, you'd want to run it on a quantum machine. But here you have a development environment, so you can build everything locally and then test it on a machine.
Yes, exactly.
Okay.
So you can create a free account on IBM, and you can actually use a real quantum computing.
Okay.
Of course, it's limited. They don't give you everything. Sometimes it's going to take a while because maybe other people are doing some testing, but you can use this on a real quantum machine. Then sharing, let's jump to the second example, which is generating words. So using binary, we can say that the letter A is going to be equal to 0, 1, 1, 0, 0, 0, 0, 1. So a single letter takes 8 bits, although the first three never change. They always remain the same. So we can create an application that takes up to 24 qubits or bits, which means 3 characters. And then we can use the PyEnchant library to just validate the words. So basically, we're going to create words with 3 letters, and we're going to check that they are actually real words. So for that, let's share my screen again. In this up. And this one is a little bit tricky because for the enchant library, which is a C library because I'm using M1 Apple machine, I need to specify where is the library located. Otherwise, it's going to give me an error. So I need to do like PyEnchant library path, and I need to say that I grabbing it from Homebrew. So when I run it, it's going to generate them. It's going to validate. And it generated 3 words: fry, hem, and jot. I wanted to generate 100, but only these 3 are valid. They look weird, but you can look up on Google that they're actually real words. So let's create another set. Sometimes it's more, sometimes it's less. It all depends, obviously. So P and THN. So 2 more words. And let's jump. And here, we're going to import again from Qiskit. We're going to import the enchant library. So here we want to have a US dictionary because we're supposedly generating words in English. We want 24 qubits and 24 bits. We're going to create our quantum circuit. So we're going to turn those bits into qubits. And for these first letters, so the ones that are going to change, we want to create a Hadamard gate for each of them. So we're going to create superposition. And we want to negate the ones that never change. So as I told you, the first 3 never change, but the first one is 0, so it doesn't matter. We're just making sure that the first 2 never change. So what it's going to change is the remaining 5. We're going to do that for the first letter, for the second letter, and for the third letter, because we want to generate 8 bits that are going to be translated into actual words. So we're going to go through each of them. We're going to measure them. So it's going to return either 0 or 1. They are. We're gonna run this for 100 shots, which is mean it's gonna try to generate 100 words. Once we have the result, we simply want to make them into words, and then we want to check that they're actually real words. So when we run it, we're gonna have a list of words that are validated and that we can see that are valid. If there's any question on this source code, it's kind of like more simple.
Yeah, so here we're essentially just generating each of the letters to put together to see if it's an actual word or not.
Yes, exactly. So we're going to use enchant library just to make sure that each generated word is actually valid.
A valid word. Okay.
Sometimes they don't look like valid, but they are. Because I try it many times. I execute this like, well, no, that cannot be a word. And I go to Google, like, okay, it's a word.
Gotcha.
Yeah, I guess the library makes this work, right? So
that was a pretty cool demo. I'm actually impressed that we got a chance to talk about quantum computing on a Wednesday morning. But I'm curious for yourself, what made you want to look into quantum computing as one of your next languages, or just for the live stream?
so I'm kind of the kind of guy that always looking for new technology, something new to learn. So
Gotcha.
when I read about quantum computing, it was like, wow, this looks pretty cool. I mean, that's awesome. And it's also kind of like brand of new. So it's always good to be kind of like on top of the wave when something is new, when you start are learning it, because once it gets like mainstream, you're ahead of people because you already know at least something about it.
Well, that's pretty cool. That's awesome. That was a great walkthrough, and I love the explanations. It was good to kind of look at a different way of computing and calculating. And what I think is really cool with quantum computing, at least what you've showed, is just the consistency of results. So if you do randomness, you know it's pure random. It's not a programmatic randomness, or even just the output. It's always going to be consistent in terms of how it operates.
Yeah, exactly. And I think we forgot to mention to like and subscribe to our YouTube channel and our Coding with Nylas show. Just give it a thumbs up. Don't forget that we have live streams every Wednesday and Friday at 11 EST and 8 PST, 8 a.m., of course, not night. You were mentioning something, yeah, regarding the movie Conjure Maria.
I thought
Yeah,
this
maybe
was your
right.
influence or inspiration for quantum computing.
Yeah, I think so.
That's awesome. This was great, Blog.
So what's coming next on Friday?
I
We're
have
doing
to
the next live
check.
stream?
I think it's something to do with visualizing your calendar using charts. So we're going to look at, I think they're called sunburst charts, and it's a way to observe your calendar in a different way. So normally when you look at your calendar, you see different time slots, but here we're going to see if we can organize it based off of how you spend your time.
Okay, that's pretty cool.
Yeah.
That's awesome.
So tune in for our next live stream on Friday.
Yep, and don't forget to check us on Twitter at nylas.com. And also, don't forget to go to our nylas.com blog where we publish two blogs per week. So just check it out and let us know if you have any questions, you want to be a guest on the show, and just enjoy the rest of your day. Thanks, Ram. Always a pleasure.
Thanks, Blog. Thank you. Bye.